Swayam Prabha. Digital India. Educated India.
Welcome back, learners. The video is for the subject of Geography for the course of Bachelor's in Arts with Geography or Bachelor's in Arts with Honours in Geography. The video is for the paper of Climatology. Today we are going to start Module 3, which is Air Pressure and Atmospheric Circulation. And today we will be starting with Lecture 1 of Module 3, which is Understanding Air Pressure and Pressure Belts of the World. The video is being recorded by Dr. Pallavi Upreti. The course coordinator and presenter for the video is Dr. Pallavi Upreti, affiliated to Department of Geography, Doon University. The academic expert and reviewer for the video is Professor Santosh Verma, Head of the Department, Department of Geography, SDM-PG Government Degree College, Doiwala, Dehradun, affiliated to Shri Dev Suman, Uttarakhand University. The video is produced and presented under the project name DTH Swayamprabha Channels of MHRD, New Delhi, India. Hello learners, I am Dr. Pallavi Upreti, Assistant Professor in the Department of Geography in Dr. Nityanand Himalayan Research and Study Center, Doon University, Dehradun. Today we are going to start Module 3 of Climatology, in which we are going to discuss atmospheric pressure and pressure belts of the world. So let's begin. In the due course of this video lecture, we will be discussing in general what is air pressure, and then we will move on to discuss what are the major factors affecting air pressure like temperature, altitude, and humidity. Then we will discuss the pressure gradients and isobars, and we will further discuss what is the horizontal distribution of air pressure and major pressure belts of the world. And finally, we will be discussing shifting of the pressure belts according to seasonal variations which are found on our planet. So this is all we are going to cover in this particular video lecture. So let's begin. We live on a planet which is surrounded by air called the atmosphere. So atmosphere is the layer of air surrounding the earth from all the sides, and atmosphere is primarily made up of several gases. Movement in the existing masses of these gases around causes weather we experience today in our day-to-day lives, and air, being a physical substance, is a mixture of several gases. So most of the gas is in form of diatomic nitrogen and oxygen with some amount of argon, helium, CO2 and other trace gases, along with the varying amount of water vapor which is also mixed in this particular composition of air found in our atmosphere. All these gas particles which are present in the atmosphere have weight, and they are pulled towards the Earth's surface because of its gravitational pull. So air has its own weight and presses against everything it touches as the gravity pulls it to the Earth's surface. Therefore, air exerts pressure through its weight, which is called as atmospheric pressure. So in simple terms, what is atmospheric pressure? Atmospheric pressure is the force which is exerted against a surface by the weight of the air above the surface. So all the gas particles that are present in the atmosphere, because they have weight, they have the tendency to get pulled toward the Earth's surface. So atmospheric pressure is actually the pressure which is exerted against the surface by the weight of the air which is above the particular surface. In order to understand the air pressure, it is important to know that it is understood in terms of existing column of air which stretches from the ground surface towards the atmosphere. So above each location on Earth is a column of air that stretches to the top of the atmosphere, and it is the weight of this column of air which is called as atmospheric pressure or air pressure. So definitely the weight of this column of air at the ground surface will be high, and it will reduce as we move up in the atmosphere. So The highest atmospheric pressure is found near the Earth's surface. Air pressure is greatest at the ground surface and decreases with altitude mainly because of two reasons. First of all, this column of air gets shorter as we move up altitudinally. And secondly is the density of these gas particles, which also reduces as we move up altitudinally. So you have more concentration of these gas particles at the ground level, and the density of these gas particles which are present in air reduces with increasing altitude. Also the length of the column of air. As you can see, the column of air when considered from the ground level stretches to higher heights. So you have more number of particles if you consider the height of the column of air taken from the ground surface. However, as we move up altitudinally, this particular length of this column of air also reduces. So definitely more particles are concentrated at the ground surface, therefore the air pressure is high. And as we move up altitudinally, the molecules which contribute to the pressure reduces, leading to low atmospheric pressure, which states that the air pressure is high at the ground surface and reduces as we move up altitudinally due to the decreased density of air particles and also because of the shortened length of the column of air which is present on any region. Air pressure is thus defined as the total weight of mass of column of air per unit of area at the sea level. So at the sea level, definitely the density of the particles is going to be very high, and also the length of this column of air is also going to be more, because of which the highest atmospheric pressure is observed over the sea level. The atmospheric pressure is maximum at sea level, which is 1034 grams per square centimeter, and this pressure is exerted in all directions, up, down, sideways also. But if the atmospheric pressure is high at the ground surface, why don't we feel that heavy atmospheric pressure upon us? It is mainly because of the fact that our bodies also exert the equal amount of pressure outward. So the air inside us exerts counter pressure from inside and balances the pressure from outside. So the exerted pressure on us from outside is counterbalanced by the exerted pressure from our bodies from inside, which balances the pressure, and therefore we do not feel the heaviness of the air pressure in general. Now, before starting the factors which affect the air pressure, let's understand how the air pressure is measured. Changes in the air pressure are measured with a very sensitive instrument called a barometer, and it is measured in millibars. Generally, the air pressure is measured in terms of height of the mercury in the glass tube, which increases with high air pressure and which reduces with low air pressure. So the standard air pressure at sea level is 1013.25 millibars at a temperature of 15 degrees Celsius and at a latitude of 45 degrees. So air pressure is definitely affected by various factors which we will just discuss in a while, and it varies from place to place. It varies in different time periods of the day also, and it may have variations across the year also. So at a sea level, at this particular temperature of 15 degrees Celsius, the air pressure is on an average 1013.25 at a latitude of 45 degrees. Now, air pressure can be shown on map with the help of isobars. So what are isobars? These are lines which on a map connect places of equal atmospheric pressure, and usually they are reduced to sea level, making the map easier to interpret. So there are regions of high pressure and there are regions of low pressure which exist in different areas. So isobar connects every area with same atmospheric pressure with a single line. So supposedly if you see this 1020 isobar, so any region which is having 1020 bar is connected by this particular isobar line. And then similarly you can see this 1016 air pressure also, and it is connected by a same line. So any two regions having same atmospheric pressure will be connected by same isobaric line, and they will depict the similar atmospheric pressure. So isobars and the study of isobar helps us in depicting the differences in air pressure which exist on our planet, and it also helps differentiate which are the areas of low pressure and which are the areas of high pressure. Factors affecting air pressure. So why do air pressure change? There are three main factors that affect the air pressure. The first one is temperature, second is altitude, third one is humidity or content of water vapor in the atmosphere. So here in this diagram you can see that all the different factors have varying impact on the air pressure. For instance, you can see that when the temperature increases, the air pressure decreases, and when the temperature decreases, air pressure increases. So there is inverse relationship between temperature and air pressure. Besides this, the impact of altitude can also be seen on air pressure. With increasing altitude, the air pressure decreases, and as the altitude decreases, the air pressure increases. Further, with water vapor content, there is also an inverse relationship. When the content of water vapor in the atmosphere increases, the air pressure decreases. And as the water vapor decreases, the air pressure increases. And finally, other factors include density, air circulation, earth rotation, and water vapor, etc. So you can observe that density has a positive relationship with air pressure. So as the density increases, the air pressure also increases, and as the density decreases, the air pressure also tend to decrease. So due to all these factors, the air pressure varies spatially, seasonally, and diagonally. Now let's discuss the major three factors which impact the air pressure one by one. First is the temperature. Temperature and air pressure are inversely proportional to each other, which means that if the temperature is high, the air pressure is going to be low, and if the temperature is low, the air pressure is going to be high. In conditions of warm temperature, the warm air is less dense, and as individual gas particles warm up, they take up more space, causing the gas to be less dense. So they exert less pressure and they move apart, become fewer and weightless, which reduces the air pressure. Hence, in high temperatures, the atmospheric pressure is low as compared to the atmospheric pressure which is high in the low temperature areas. So when the temperature is low, the cold air, because it is dense, the molecules moves very slowly and are compacted together, which exerts more pressure leading to high pressure conditions. So the temperature shares inversely proportional relationship with the air pressure. Now, besides temperature, the altitude also shares inverse relationship with the air pressure. Now, as the air pressure is greatest at the ground surface, and with increasing altitude, the air pressure also decreases, both because of the column of air gets shorter as we move up, and also because of the density of gas particles decreases with altitude. So air pressure is high at lower altitudes. Why? Because you have more dense air which exerts more pressure, and air pressure is low at higher altitudes because of less dense air with more spaces between the air molecules, and hence the air pressure is low. So there is less oxygen also to breathe at the top of a mountain, mainly because of the low air density, which also means low quantity of oxygen. So people experience difficulty in breathing as we move up altitudinally. So why do we experience uncomfortableness when we travel to any mountainous area or any high altitudinal area? So as the altitude increases, the amount of gas molecules in the air decreases. The air becomes less dense than the air near to the sea level. So if one moves from the lower altitudinal area to any higher altitudinal area, the air pressure decreases. And as the air pressure decreases, the air becomes thinner and thinner. So the thin outside air exerts less pressure on our bodies as compared to the pressure exerted on our bodies when we were located at a low altitudinal area. So the thin outside air exerts less pressure on our bodies, but our bodies still exerts the same pressure towards the outside walls of our body as they were exerting to counterbalance the air pressure when we were located at the lower latitudes. But as we move to the higher altitudes, the air pressure decreases around us, exerting less pressure on our bodies, but our bodies still keep on exerting the same amount of pressure, making us uncomfortable and creating conditions of uneasiness for us. People may experience popping of their ears, breathlessness with occasional headaches if we don't give enough time for our bodies to adjust to that decreased air pressure with increasing altitude. Now, the air pressure also shares inverse relationship with humidity also. So as the air gets warmer and it tends to rise, it gets more water vapor and atmospheric pressure decreases because warm, humid air is less dense, leading to low pressure. But if the air is dry and as the gas in the atmosphere cools down, it loses the water vapor to precipitation, because of which the dry, cool air is more dense and increases the atmospheric pressure. So considering all the factors which we have discussed above, uneven heating and temperature conditions and varying amount of water vapor in the atmosphere results in regions of high pressure and low pressure. These pressure differential causes air to move along the ground from the regions of high pressure towards the regions of low pressure, and we experience these air currents as winds. So winds always move from the high pressure regions towards the low pressure regions. But the movement, the direction and the velocity of winds between the high pressure regions to the low pressure regions is governed by the pressure gradient force, which is the rate at which the temperature changes from one region to another. So the higher the pressure gradient force, the more the velocity of winds will be, and the lower the pressure gradient force, the lower the velocity of winds will be. So pressure gradient force is actually the force which arises because of the differences in the pressure conditions of different regions, which finally derives the winds from the high pressure areas towards the low pressure areas. So the difference between the high pressure and low pressure can be profound sometimes. In atmospheric sciences, the pressure gradient is the physical quantity that describes in which direction and at what rate the pressure increases most rapidly around a particular location. So it's a way to describe the differences in the atmospheric pressure from one location to another, from high pressure to low pressure, and from regions of low pressure to high pressure. So a pressure gradient is the rate of change of atmospheric pressure with regard to the horizontal distance at a given point in time, and it is generally shown with the help of isobars. So isobars are the lines which join the areas of equal air pressure on map, so that it is convenient for us to understand what type of pressure exists in which regions of the world. Strong pressure gradient is depicted by closely spaced isobar. So as you can see in the map also, that these regions of the world show very closely spaced isobar, which depict that the pressure gradient is very high. That is, there is a steep increase or decrease in the pressure conditions in these areas as compared to other regions of the world where isobars are widely spaced. So widely spaced isobars reflect that the rate of change of pressure is gradual, while closely spaced isobars depict that the rate of change of pressure in those regions is very steep. The force driving the currents caused by the pressure differences between the two regions is called as pressure gradient. It defines the differences in pressure which exist between the high pressure regions and low pressure regions and consequent movement of air from high pressure regions to low pressure regions. So air masses moved by this pressure gradient difference transfer heat by conduction as cooler gas particles move into the region containing the warmer gas particles. So it is similar to the small contained conduction cycle which is present in the room which is heated from one side, where you can see that the warm air from the heat source rises up and it moves across the ceiling, and in the process it cools down and it sinks. So as it sinks, the cool air returns along the ground towards the heat source, completing the cycle. But similar kind of phenomena also occurs in the atmosphere, but since the system is more open, so the rising and falling of air mass causes movement in many directions. The movement of air up around the region of low pressure causes air masses to converge at the ground surface and diverge high up in the atmosphere because of existing high pressure in the upper atmosphere. The opposite happens around the region of high pressure where winds diverge near the ground surface, where the wind sinks from the upper atmosphere and diverge at the ground surface, and they converge at the upper atmospheric regions because of the presence of low pressure in the upper atmosphere. So you have opposite conditions. If you have high pressure at the ground surface, you have low pressure at the upper atmosphere, and if you have low pressure at the ground surface, you have high pressure at the upper atmosphere. So high pressure regions are characterized by divergence of winds, whereas the low pressure regions are characterized by convergence of winds. So as you can see in the map of USA also, that areas of low pressure center exist as well as the area of high pressure center exists. So the winds always move from the high pressure areas towards the low pressure areas following the pressure gradients. So as you can see in the eastern region of this map, the pressure gradient is very steep, and there is steep fall in air pressure as compared to the western region. So the velocity of winds in the western region towards the low pressure center will be gentle as compared to the eastern region, where because of the extreme pressure gradient, the velocity of winds will be high, and the direction of winds will always be from high pressure regions towards the low pressure centers. So in this case, the low pressure centers demarcate the convergence of winds coming from the high pressure areas at the ground level, whereas the high pressure areas are characterized by the divergence of winds at the ground surface. So pressure gradients do not only demarcate the velocity of winds, but also the direction of winds from high pressure areas towards the low pressure center areas at the ground level, and opposite exits at the upper atmospheric level for both the areas. Pressure gradient also shares close relationship with wind circulation. It defines the circulation of winds because the winds blow from the high pressure regions towards the low pressure regions following a barometric slope. So it defines the direction as well as speed of wind. If the pressure gradient is very steep, then there will be high speed of winds blowing from the high pressure regions towards the low pressure regions, and in these areas the isobars will be very closely spaced. But if the pressure gradient is gradual, in that case light winds may blow from high pressure regions towards the low pressure regions, and the isobars in these areas will also be widely spaced. So the stronger the pressure gradients force with more closely packed isobars, the stronger flow of winds will exist in those regions. So closely spaced isobars mean stronger winds, whereas loosely spaced isobars show less pressure gradient and associated with the gentle wind movement in the areas. Just observe this map. A steep pressure gradient shown in this map reflects that the wind speed will be very high in this area as compared to the adjoining area where you can see that isobars are loosely spaced. So the wind speed in this area will be comparatively of gentle nature. Now, the horizontal distribution of air pressure is generally studied on the basis of isobars. So isobars, as we have studied in the earlier slide, is the line which joins the places of equal air pressure. So based on the study of these isobars, the air pressure on the globe can be divided into broad two categories. That is, the regions having low air pressure, which are characterized by cyclonic conditions, and they are also called as depressions. And then you have the regions of high pressure, which are characterized by anticyclonic conditions, which are also called as highs, and they are also called as depressions. So if you have low pressure conditions on the ground surface, the winds have the tendency to converge towards that low pressure center, but winds do not aggregate at that low pressure center. So wherever you have a low pressure center at the ground surface, there is convergence of winds, and these winds, once they converge, they tend to rise up, wherein they again diverge in the upper atmosphere due to the existing high pressure conditions. So you have opposite conditions. If you have low pressure conditions on the ground surface, you will have high pressure conditions in the upper atmosphere. Similarly, if you have high pressure conditions on the ground surface, it will lead to divergence of winds on the ground surface, but opposite to it, in the upper atmosphere, you have convergence of winds characterized by sinking air. And this sinking air, once hits the ground, because of high pressure, they tend to diverge from the center of high pressure towards the region of low pressure. So they are attracted towards the low pressure centers from the high pressure areas. So on the ground surface, the movement of winds is always from high pressure towards the low pressure. And you have opposite conditions in the upper atmosphere. So as you can see in this animation also, the winds in the low pressure center are converging towards this low pressure center and continuously rising towards the upper atmosphere, where they are again diverging due to the existing high pressure center, and the winds from this high pressure center in the upper atmosphere are again attracted towards the low pressure center, which exists in the upper atmosphere only. And once the winds are attracted towards this low pressure center in the upper atmosphere, they tend to sink towards the high pressure center at the ground surface. And again, from this high pressure center, the winds move towards the low pressure center at the ground surface. So this whole complete circulation from high pressure to low pressure is always working in the atmosphere and leading to the distribution of heat on the Earth's surface. Now, air is the function of various factors, as we have studied in the earlier slides also. It is affected by temperature, humidity, altitude, and several other factors also. So if we look at the globe, then it appears that there is a definite system of high and low pressure. For generalization, if the globe is considered to be homogeneous, either land or water, then there should be regular and systematic zonal distribution of high and low pressure. But the regularity of pressure belts is disturbed due to the unequal distribution of land and water on globe. So due to unequal distribution of land and water, and because of their differential properties of heating and cooling, there is unequal distribution of air pressure. The pressure belt seems to be discontinuous in the northern hemisphere with several embedded low pressure centers, as you can see in this diagram also. And then the pressure belts are more or less regular in the southern hemisphere because of more percentage of water area in the southern hemisphere as compared to northern hemisphere.
hemisphere. So there is no basic definite trend of distribution of pressure from equator towards the poles. If the air pressure would have been just the function of temperature, then there should have been regular increase in the pressure belts poleward because the temperature regularly decreases from the equator towards the polar regions. But this is not the case. There is low pressure near the equator, which is mainly because of the temperature conditions, and then there is low pressure even which is found at somewhere around 50 to 70 degree latitudes also. But the temperature in those regions is not very high. So definitely the low pressure in 50 to 60 degree latitudes is manifested by factors other than temperature. So you can say that while few air pressure belts are thermally induced, other belts are dynamically induced. That is, they are induced because of factors other than the temperature. So there is unequal distribution of air pressure on the globe. As you can see in these maps of January and July also, the trend of air pressure changes, which happens with the seasons around the year. So the horizontal distribution of air pressure across the latitudes is definitely characterized by highs and low pressure belts, and there is a distinctively identifiable zone of horizontal air pressure regime which are called as pressure belts, which are observed around the globe. So in totality, there are 7 pressure belts on the globe which are characterized on the basis of mode of genesis, that is whether they are thermally induced or induced because of other factors. And based on this mode of genesis, they are divided into 2 broad categories. First is the thermally induced pressure belt. So pressure belts which originate primarily because of the temperature conditions in those areas are called the thermally induced belt. So this include the equatorial low pressure belt and polar high pressure belt. So equatorial low pressure belt is located right at equator, and polar high pressure belts is located in the northern and southern polar areas also. So you can clearly see that equatorial areas will definitely have very high temperature. So the particular low pressure belt is induced here, and the polar areas will definitely have very low temperature. So a distinctively high pressure belt exists in northern polar regions and southern polar regions also. So these two belts are thermally induced, while we have other category of belts also which are dynamically induced because of factors other than thermal conditions, like the rotation of earth plays a great role in development of these particular two belts. So you have subtropical high pressure belt which is located above the equatorial low pressure belt in both the hemisphere, and then you also have subpolar low pressure belt which is located around 66.5 degree north and south in both the hemispheres. So we will discuss all these belts in detail, but just understand that these 7 belts are created because of two major reasons. First is because of temperature, and second is because of factors other than temperatures which exist on the surface of Earth. So in total, you can see that you have 1 equatorial belt, 2 subtropical high pressure belts, 2 subpolar low pressure belts, one in the northern hemisphere, other in the southern hemisphere, and again you have 2 polar high pressure belts. So in totality, you have 7 air pressure belts which demarcate the horizontal distribution of air pressure on the globe across the latitudes. Now let's start the horizontal distribution of air pressure with equatorial low pressure belt. So equatorial low pressure belt is located on both the sides of geographical equator. So you have equator at 0 degree latitude, and this belt extends from 5 degree north to 5 degrees south latitude on both the sides of geographical equator, and this belt is thermally induced because the ground surface is intensely heated during the day due to the almost vertical sun rays, and thus the lowermost layer of the air coming in contact with the heated ground surface also gets warmed up, which leads to the formation of low pressure in these regions. So high temperature areas are always demarcated by the low pressure. So as the air warms and it expands, it becomes light and consequently it rises up to the upper atmosphere, creating low pressure in these zones. So the low air pressure in these areas is mainly induced because of intensive heating of land, intensive insolation in these areas, and consequently the formation of low pressure zones in these particular areas. So these equatorial low pressure areas, because they have low pressure at the ground surface, they are characterized by convergence of winds at the ground surface and consequent rising of these winds along this particular area, where they finally ascend and diverge in the upper atmospheric regions due to the existing high pressure. So these areas are characterized by low pressure and convergence of winds at the ground surface and aloft divergence due to the existence of high pressure in the upper atmospheric regions above these low pressure areas. Besides this, these equatorial low pressure belts are also characterized by shifting of the existing low air pressure belt. So the location of the equatorial low pressure belt between 5° north to 5° south is not stationary because there is a seasonal apparent movement of the sun. So when the sun is overhead the Tropic of Cancer, the air pressure belt may shift to 10 to 20° in the northern hemisphere. But with the seasonal migration of sun towards the southern hemisphere when it is above the Tropic of Capricorn, the belt may shift towards the 10 to 20° in the southern hemisphere also. So this belt is characterized by the seasonal migration. So it migrates northward when the sun is overhead the Tropic of Cancer and southward when the sun is over the Tropic of Capricorn. So winds coming from all the direction, they try to converge to this low pressure belt, and once they converge, they uplift and they diverge in the upper atmospheric region. So equatorial regions are actually characterized by low pressure belts which are thermally induced mainly because of intensive insolation in these regions. Now, on moving away from the equatorial regions towards the polar regions, we have subtropical high pressure belts, and these regions are also called as horse latitudes. So, the subtropical high pressure belt extends from 25 to 35° latitudes in both the hemisphere. And it is important to note that this particular high pressure belt is not thermally induced because this zone, besides 2 to 3 winter months, fairly receives very high temperature throughout the year. So if you consider just the temperature, the particular belt should have been a low pressure belt because these regions of the world receive fairly high temperature throughout the year. But this particular belt is not thermally induced, it is dynamically induced, therefore it is a high pressure belt. And how it is dynamically induced? Mainly because of the rotation of the earth and sinking and settling down of winds in these regions. So the winds which actually rises from the low pressure areas, from the equatorial areas and other low pressure areas on the globe, they tend to settle in these areas, leading to high pressure conditions on the ground surface. So these areas represent the surface wind divergence and aloft convergence. So the winds in these regions actually are characterized by the sinking of air, and because of high pressure at the ground surface, they tend to diverge from the center toward outside margins, because of which the atmospheric stability exists in these areas, anticyclonic conditions in these areas receives very less rainfall, and aridity is one of the common feature which is seen along this particular belt. So this region experience very short winters and fairly high temperature throughout the year. And because of the prevalence of anticyclonic conditions, these areas are very calm areas also, with almost very low mobility of air. And therefore, the major hot deserts of the world are located in the western parts of the continent in these zones only, which extend from 25 to 35° latitude in both the hemisphere. So you can see in this map also Just observe the location of major deserts of the world in the 25° to 35° north and south of the equator. So you can see that the concentration of desert towards the western margins of the continents in this particular belt is very high as compared to any other latitude on the earth, because these regions are characterized by sinking of air from aloft and divergence of winds at the ground surface that lead to atmospheric stability, and therefore arid conditions exist in these areas, leading to formation of hot deserts in these areas. Now the third air pressure belt is subpolar low pressure belt. This particular belt is located between 60 to 65° latitude in both the hemisphere, and the low pressure belt does not appear to be thermally induced, although it is located in very high latitudes, but it is not thermally induced. The temperature in these regions is low throughout the year, and as such there should have been a high pressure belt instead of low pressure belt. But it is obvious that there is a low pressure belt in these regions, and therefore it is not induced because of the temperature conditions. Therefore this belt is dynamically induced, mainly because the surface air spreads outwards from this zone due to the rotation of Earth, and low pressure belt is created in these regions. It is important to understand that if the rotation of Earth would have been the main factor to demarcate the low pressure in these areas, so the rotation factor should be more dominant in the polar areas, which are just located at 90° latitude north and south of the equator. But in those areas, the exceptionally low temperature overshadow the rotation effect, and therefore the polar high pressure belt or the high pressure belt in the polar areas, which should have been actually a low pressure belt if you just consider the rotation factor, but the high pressure belt which is existing in the polar areas is mainly because of the temperature. Why? Because the temperature overshadow every other factor which is existing in those areas, and therefore a high pressure exists in the polar areas. But in these subpolar low pressure belt areas, although the temperature is low and the pressure belt should have been high, but the rotation factor is so pronounced that the air is thrown outwards and it's spread outwards, leading to the formation of low pressure zone. And it is more developed and regular in the southern hemisphere, and it is less developed in the northern hemisphere, again because of the over dominance of water in the southern hemisphere as compared to the northern hemisphere. So this particular belt in the northern hemisphere, instead of a regular continuous belt, is characterized by embedded low pressure centers, especially during the summer seasons in the northern hemisphere, mainly because of the great contrast of the temperatures of the continents and the ocean during the northern summers. The low pressure belts become discontinuous, and it is found in a few low pressure cells, while the temperature contrast between the continents and the ocean is much reduced during the winter season, and hence the low pressure belt become more or less regular and continuous in the northern hemisphere during the winter season. Now, the fourth important pressure belt is the polar high pressure belt. So, high pressure persists at the poles throughout the year because of prevalence of very low temperature. So, this polar high pressure belt is again thermally induced, and the main dominating factor in the formation of this belt is temperature, which overshadows every other factor like the rotation of Earth in these areas. And because of exceptionally low temperature, the polar high pressure belt is created between 70 to 90° latitudes in both the hemispheres. This particular belt is thermally induced because of existing extremely cold conditions and very low temperature, wherein the low temperature makes the air dense and it sinks, creating a high pressure region in both the hemispheres. So the diurnal rotating effect also exists parallelly, spreading out the layer outward, causing thinning of air. But this is overshadowed by the existing temperature conditions, which are very low throughout the year, and hence the high pressure in these zones is created primarily because of the extremely low temperatures. Therefore, the polar high pressure belt is primarily thermally induced. So you have two belts which are thermally induced. First one is the equatorial low pressure belt, and then you have the polar high pressure belt which is thermally induced. And then you have the subtropical high pressure belt and also the subpolar low pressure belt which are dynamically induced. So you have two categories of pressure belts which define the horizontal distribution of air pressure, and these belts are 7 in number which are spread latitudinally, defining the horizontal distribution of air pressure on the earth. So these are the pressure belts in totality. You can see that the equatorial low pressure belts extend to 5 degrees north and 5 degrees south of the equator. And then you have the subtropical high pressure belts which exist along the Tropic of Cancer in the northern hemisphere and Tropic of Capricorn in the southern hemisphere. And these areas are also called as mid-latitudinal high pressure areas. And beyond 35 to 40 degrees, you have subpolar low pressure belts which extend from somewhere around 60 to 65 degree in both the hemisphere. And finally, you have the polar high pressure belt which extend from somewhere around 70 to 90 degrees in both the hemispheres. So here you can see that while polar high pressure belt 1 and equatorial low pressure belt 2, these two pressure belts are thermally induced, while the belts which are found in the center of these two particular belts are dynamically induced. So subpolar low pressure belt and then the subtropical high pressure belt in both the hemispheres is also dynamically induced, while the equatorial low pressure belt and also the polar high pressure belt is thermally induced. Now, it is important to note that the pressure belts which we have studied just now are not stationary. They tend to shift from time to time depending upon the apparent movement of the sun. So let's discuss the shifting of pressure belts on the globe. With the apparent northward and southward movement of the sun, the temperature condition fluctuates in both the hemisphere and the air pressure also shifts. The shifting of the pressure belts causes seasonal changes in the climate, especially between 30 to 40 degrees in both the hemisphere where their impact is very pronounced. So when the sun is over the Tropic of Cancer, all the pressure belts except the polar high pressure belt shifts northward, while when the sun is over the Tropic of Capricorn, all the pressure belts shift southward except the polar high pressure belt. So let's just try to understand the shifting of pressure belts from the next animation. Now, as we know that Earth is tilted at 23.5 degrees and it is constantly rotating on its axis, we also know that besides rotation, the Earth is also revolving around the sun throughout the year, which causes different seasons which we experience on our planet. So, when the tilted northern side of Earth faces the sun at this time period is exactly above the Tropic of Cancer, and we have summers in the northern hemisphere. But opposite to this, at this point of time period, the sun is far away from the Tropic of Capricorn and Antarctic Circle. So we have winters in the southern hemisphere. Opposite to this, further when the revolution continues, we have September equinox, where we have sun which is shining above the equator, and you have falls in the northern hemisphere while you have springs in the southern hemisphere. And again during the December solstice, we have the tilted southern part of Earth facing the sun. So at this point of time, the sun is directly overhead the Tropic of Capricorn. So you have summers in the southern hemisphere, and opposite to this, because the sun is very much far away from the Tropic of Cancer and Arctic Circle, we have winters in the northern hemisphere. And as the revolution continues further, we experience March equinox when sun moves back again to the equatorial region. So at this point of time, you have springs in the northern hemisphere and fall in the southern hemisphere. So all this time period when the earth is constantly revolving around the sun and you experience different seasons on earth, there is a seasonal shift also in the pressure belts which is experienced around the globe. So during the vernal equinox, that is the March time period, and the autumn equinox, that is the September time period, the sun is directly over the equator, and hence all the pressure belts are also stationed accordingly. But as the sun moves northward during the summer solstice over the Tropic of Cancer, just observe the pressure belts also move northward with the apparent movement of the sun. And as the sun comes back above the equatorial area during the vernal equinox or autumn equinox, the pressure belts also shift accordingly southward with the apparent movement of the sun. And finally, when during the winter solstice, the sun is directly over the Tropic of Capricorn, the pressure belts also tend to shift southward with the apparent movement of the sun. So, as the sun progresses from the Tropic of Cancer to the Tropic of Capricorn with its apparent movement, the pressure belts around the world also shift either northward or southward depending upon the summer solstice or winter solstice. This shifting of pressure belts of the world is very, very important with respect to the movement of wind circulation, the existence of several weather patterns and climatic conditions which exist in different regions of the world. But as you might have observed in this particular animation, that all the pressure belts move with the apparent movement of the sun, but polar high pressure belts remain stationary throughout the year and do not fluctuate with the movement of sun. So the shifting of these pressure belts is associated with the dynamic character of the Earth's climate, and these pressure belts have significant impact on the weather conditions and changing climatic conditions along different regions of the world in different seasons which we experience throughout the year. So pressure belts and their northward and southward shifting with the apparent movement of the sun is one of the most important phenomena which govern various atmospheric conditions which exist on our planet. So it is very, very important. So summarizing the video now, atmospheric pressure is the force exerted against a surface by the weight of the air above it. The air pressure can be low and it can be high and may differ spatially, diurnally and horizontally depending upon factors like temperature, altitude, humidity, water vapor content, density, etc. The differences in the air pressure leads to the movement of winds which blow from high pressure areas towards the low pressure areas, and the horizontal distribution of air pressure can be thermally and dynamically induced. So based on the mode of genesis, you have 7 types of pressure belts, out of which the equatorial low pressure belt and polar high pressure belt are thermally induced, while the subtropical high pressure belts, which is again found in both the hemispheres, and subpolar low pressure belts, which is also found again in both the hemispheres, is dynamically induced. So in total, you have 7 pressure belts, in which only equatorial low pressure belt is single belt, and besides equatorial low pressure belts, all the other belts are found in both the hemispheres. So you have in total of 7 pressure belts. So the pressure belt shifts with the apparent annual movement of the sun as the earth revolves around the sun over the period of 1 year, and this shifting of pressure belts impact the global climatic and weather conditions which we experience in different regions of the world. So in total, the atmospheric pressure is one of the important atmospheric phenomena which exist on our planet, and it is associated with numerous factors which govern in total the atmospheric conditions on Earth, impacting the global climatic conditions in different regions of the world. So I hope the video was informative. Thank you for listening.